Okay, folks, so we're going to get started on this fourth section. It's going to deal with exponential growth and decay. We graphed exponential growth and exponential decay functions last time. We're going to use those. I mean, the vast majority of these problems are going to be just word problems. Okay, so we're going to be moving our way through that. Okay, we have three different learning targets. One of it, which we've actually already used, that's identifying functions as exponential or not. We'll just recap that because it's a pretty important concept for what we're doing. Then we're going to be able to identify key features, and we'll discuss what those are, and then also using those to solve real life problems. And that's exactly how I'll try to grade these moving forward. Okay. Just like before, though, you will need a calculator. Like we talked about, you'll just need one every day. All right. Let's go ahead and start with this. Okay, first target is you're going to be able to identify key features of exponential growth and exponential decay functions. There is a little typo here. So exponential growth is when the quantity increases by the same factor over an equal amount of intervals of time. And exponential decay is when it decreases. So to me, it's pretty obvious that increases is growth and then decreases is decay. Okay, what each of these are missing is an A value right outside of the parentheses. I forgot to type in there, so I got it typed in this morning. That was a little too late. Okay. Okay. Here are basically your key features. Okay, Y is going to be the amount you'll get a time amount to find these out at, and your Y, when you plug in X will be time, which, okay, that's one of our key features. After X, time, Y is like the amount. It's kind of like your total. A lot of times it is just going to be like a total amount. Okay. R is going to be the rate increase or decrease as a decimal. Okay, so rate for us is going to be percentage. R, though, we need to write that percentage as a decimal. X is, in this situation, going to be time. Sometimes you're going to see this written as T. So when you go take your Iowa assessments next week, it's not going to blow my mind if you see something like this and instead of X it has T. It'll function the exact same. It's just T for time, sometimes X for time. And then the last one that I didn't write, which is our A value. Which is just like your initial or your starting amount. Knowing these things are going to be helpful not only for learning target 15, but also for the word problem learning targets, where you're using these to solve real life problems. You're going to need to know what those all mean because they're going to have some meaning within the problem. Okay. First off, as I look at 1A and 1B, I want to find the percent rate of change and the initial value. It might be helpful to be able to identify 1A and 1B as growth or decay. Does anybody remember how to identify one of these as growth or as decay. We did that. That was one of our transformations. So in the previous section, we found A, B, H, and K. How could we tell if it was growth or decay? Yeah. B value is what? Not positive or negative, but you're really close. It is this B value. It's what? Nope. Greater than or less than 1. So this one's greater than 1. So is it growth or decay? Okay, so this is a growth function. Okay, so I know that this is growth. So I'm looking at growth, and I want to find the rate of growth. Okay. So if I want to find the rate of growth, notice that the growth formula has 1 plus R. Right? So here, this right here tells me that this is my growth. And I know growth can be rewritten as 1 plus R. Everybody follow what I have there so far? B value determines growth. So that means that this right here is my B value. So they can be equal to each other. How do I solve for R here? Thought I heard somebody say it. 1 plus R. How do I solve for R? -1. -1? So my R value is 0.07. Anybody know how to figure that out as a percentage? Times it by 100. So for me, this is 7% growth. So R is 7% growth. Because R is the percent rate of change. Okay, initial value. What's my initial value? Now look at the description above. What letter is it? What letter is my initial value? A. What number's in the A spot? 5. So what's the initial value? 5. We don't know what we're talking about, but it's 5 something. Okay, questions about 1A? Okay, 1B. When I'm looking at 1B, is this going to be a growth or decay function? Decay, because the B value is less than 1. So this is a decay function. So now I know that these two things are the same. Okay, so I know 0.98 is equal to 1 minus R. How do you solve for R? No, I'm not going to plus 1 because the minus is attached to the R. Okay, you want to say that again? Yeah, the minus sign's with the R. So now I have negative 0.02 is equal to negative R. And then I would divide by -1. Get 0.02 is equal to R. So that's my rate as a decimal, which is very important. But what's my decay as a percentage? This is 2% decay. So this is a 2% decay. You know, for me, I honestly don't have to do this. Because I look, it's 0.07 bigger than 0.07 bigger than 1 growth. It's 0.02 less than 1 decay. So if I showed you how to do it by hand, I would say this is the long way. If you can just look at it and can just tell, that's totally fine. Okay, there's nothing wrong with that. In fact, I would probably encourage that if that's something you're comfortable with. And what's my initial amount? 0.2. Okay. Questions about that? All right, let's take a second. Try monitoring progress 1 and 2. We're going to try to get through the whole section today. So we're going to try to keep a healthy, steady pace here today. Hey, so here again, I think it's very possible that everybody's going to be able to figure your percent growth or decay without having to write and solve an equation. I'm 0.01 larger than 1, so it's growth, and 0.01 as a percentage is 1%. So this equation has 1% growth per 1x value. Okay, A value is 0.9, so that's the starting amount or the initial value. Okay, on monitoring progress 2, 0.77 is 0.23 less than 1. Since it's 0.23 less than 1, it's 23% decay. So this 2 is going to lose 23% of its value every single 1x value. And then my A value is 2. So my starting amount is 2. All right. Any questions about those 4? Okay. So now what we're going to do is actually this is the same as what we did before. Okay. The only difference is I think our only options are exponential growth or decay. So we're going to know that these are exponential. But then what I want to do is determine what is the growth or decay percentage. Okay, first off, looking at 2a, looking at the y values, do you feel like it's a growth function or a decay function? It's decay. Okay, we feel like it's a decay function. So what we're going to do is we are going to figure out how much. Okay, so this is +1, +1, +1. That's good. What's happening in the y values? Okay, it is decreasing by what? Dividing by 3 though, right? Dividing by 3 is the same as multiplying by what though? 1/3. 1/3. So this is the same as times by 1/3. Good. So this is decay. Hey, let's do a little bit extra with this though. So what's my percent decrease? If I'm multiplying by 1/3 or I'm dividing by 3 over, what's my percent decrease? 33, and I'm going to go 0.3 repeated. 33.3 repeated. Right? Because for every 1x this goes up, this goes down by 1/3. So this has a 33% decay. So what's my R value? For 33%. 33.3%. That's what the B value would be. But I just want to know what's the R value? What's the, how do I rewrite 33.3% as a decimal? 0.33. Okay. So then what's the A value? What's the starting amount? What X value is kind of the starting value typically? 0. Okay. And what Y value do we start at 0? So what do we think the A value is? 270. I have enough information to actually write the equation. Right? Y equals, well, this is a decay function. A, so 270 times one minus R. So 1 minus 0.33, the X power. And as you said a moment ago, it's 0.67, right? Well, 1 minus 0.33 is 0.67. So this can be simplified into 270 times 0.67, the X power. This equation represents this data set. Okay, now what I just showed you, all this extra stuff, not necessarily a requirement, but I think it's pretty beneficial to do. Okay, let's look at B. Okay, looking at the X values, they're all going up by 1. What's happening to the Y values? So is this growth or decay? Anybody think they know what the rate is? 150%? No, it's not 150%. No. Doubling will have a 100% growth rate. I believe. I should double check. Yeah. So if it has a 100% growth rate, right? Because it's doubling, it's taking 100% of 5 and going to it, and then 100% of 10 and going to it. What's the rate then? Rate of change, or the percent rate? How do I write 100 as a decimal? 1. What's my starting value? 5. So then I'm going to use my growth formula. That's in the very top left of our paper. Okay, and it's going to be Y equals 5 times 1 plus 1, the X power. So this will be Y equals 5 times 2 to the X power. So 100% growth is doubling. What would tripling be? Tripling is actually 200% growth. What would quadrupling be? 300% growth. What would multiplying by 5 be? 400% growth. It's weird how that works. It even throws me off if you come down. Hey, this is what I want you to do for monitoring progress. Just figure out if it's growth or decay. That's all this is really asking for you. But then have one person next to you write the equation for 3, and then you write the equation for 4, and then just kind of compare with each other. Okay. So I wrote the equation down here by finding the R and the eta. That's what 144 is. 4/9. One doesn't that. Yeah. You're gonna have to figure it out. We take 1/4. Okay, folks. Yeah, sure. Okay. 3 on 3. My decay is 25% because 25% is the same as a 1/4, right? So my rate of decay is 0.25. Okay. I think it's because we were so hung up on doubling is 100% growth and tripling is 200% growth. But when it comes to decay actually is a little bit more straightforward. Your rate of change is like your fraction you're multiplying by. Okay. All right. Okay. Any questions? I feel like the weirdest part of all of this is that multiplying by 3 is 200% growth. All right. All right, let's go to the next page. Now we're going to get into the good stuff. We're going to start using exponent, properties of exponents to solve real problems. That's a learning target from a long time ago. Okay, realistically, what it means is you're going to be able to use exponential growth, exponential decay, and then also compound interest. Okay. All right, exponential functions are used in real life involving compound interest, though interest is expressed as an annual, which means what? What does annually mean? Not quite. Every time, how often though? Every year, okay? So interest is typically given as an annual rate. So you go to a bank and they're going to give you an annual yearly % growth, okay? The interest is compounded more frequently than that. So it's not going to compound every year. Okay. So the formula, we forgot the A here again. Y equals A times 1 plus R to the X power must be modified for compound interest problems. Okay. Compound interest is the interest earned on the principal, not Mr. Bergevak or Ms. Nab. Principal is the amount of money you put into an account, the initial deposit, and on previously earned interest. The balance Y of an account is expressed by, and once again, we have another typo, N times X power. Okay, so let's break down all these different parts of this formula. Okay, principal, P. I think this is the wrong spelling of principal. Perfect. That's all right. I think it's principal with an LE and not a AL. This is the principal. With it's the initial amount. It is the exact same thing as A on the previous page. There's no difference between capital P principal and A. It's just typically compound interest will be used with finances or money. Okay, R is the I should write percent, right? But we write it as a decimal. That is the exact same thing as the previous page. Technically, this is the same formula. It's just you have to kind of adjust it. Okay, X is time. Again, you are often going to see that X written as just a T. And then N, this is the weird one or the new one. Number of times compounded in a year. Okay. There are other things besides money that can grow exponentially. And as a matter of fact, we can, in Algebra 2, someday you'll learn about continuous growth. You know, if you think about the way a tree grows, it doesn't grow once a day and it just shoots up an inch every day. It's continuously growing, and you'll learn about that. But right now we got to learn how things grow in intervals. Okay. Any questions besides all the... This is what happens when Mrs. Scar goes on maternity leave and I don't have anybody to proofread my work. So, all right. Example 3A. What might be difficult for you at times is understanding we have 3 formulas: compound interest, regular growth, and regular decay. I think identifying the difference between growth and decay is going to be easy. I think sometimes identifying when is it compounded growth and when is it regular exponential growth might be an issue at times, but luckily there's a word that we're going to look for. Okay. 3A, you deposit $100 in a savings account that earns 6% annual interest compounded monthly. Write a function that represents the balance after X years. Okay. Earns, growth or decay. If I'm earning money, 6% of my money, growth. Now it's a matter, is it regular exponential growth, where it's only happening one time every year? Or is it compounded growth, where it's happening more than one time every year? Am I only earning money once every year, or am I earning money more than one time every year? More than one time, because it's compounded monthly. This is going to be a compound interest formula problem. This is going to be a compound interest thing. Okay. Everybody understand how I came to that conclusion that that's the formula I need to use. I'll have the formulas available for everybody. You don't have to have them memorized, but you need to know which one is which. Okay, or which one to use and what all the different letters mean. Okay, it's capital P. Capital P is the principal, the initial amount of money I put in. What's that? $100. R, the rate. What percentage am I using? Okay, 6%. That's good, but we need the decimal. Okay, so 0.06. Yep. Take that number divided by 100. That would be your percentage. What's the next one we have? X is time. We don't really have that, so that's okay. We need N. Number of times compounded in a year. It would be 12. How come it's 12? 12 months in a year and it's compounded monthly. Okay. What if it said compounded quarterly? How many times? No. Quarterly. Oh. How many quarters are in a dollar? 4. 4. So quarterly would be 4 times. All right. What if it said compounded every 3 months? Still 4, because there's 3 months, 4 times in a year. What if it said compounded every 2 months? Be 6. What if I said compounded every 6 months? 2. Okay. How many times does it happen in a year? All right, good. Hey, I think that's the hard part. We're just using the formula. Okay. At least at this point here, what I like to do is I personally like to write the formula down. You write it down enough times, you're going to have some general understanding about it. And then we're just going to start replacing the numbers. Okay. So, Y equals P. What number is P? 100 times 1 plus R divided by N. So R is 0.06 divided by N. What's N? To the N times X power. So what's N? 12. Good. Okay. Now all we have to do is simplify a little bit. This is random for me. Okay. This isn't like a general rule. Let's say when you round to 4 decimal points. I'm arbitrarily picking that. Okay. We could have done 2, we could have done 3. I think 4 is going to give us a fairly accurate number. Okay. I don't know if we're after around here or not. Let's find out. Okay. So now what I'm going to do is I'm going to figure out what 0.06 divided by 12 is. Oh, okay, so that ended up being pretty nice. 0.005. Well, the next part's pretty easy. 1 plus 0.005. Okay. All right, we're going to use a little exponent property here. So is everybody good at getting to this point? Okay, this is 100% acceptable in my class. If this is as far as you get, that's totally fine. I will accept it. I will give you 100% if you're able to do that accurately. The next thing I'm going to show you, though, is just a little trick using exponent properties so we can compare exponential growth equations pretty easily. Okay? Power to power rule. Anybody happen to remember that? When I have an exponent raised to a second exponent, what do? Multiply them. So what I can do is I can take this equation and go 1.005 to the 12th power to the x power. Because we have 12 times x, power to power tells me I can split it up then. I'm just using that property in reverse. Then I'm going to take 1.005. I'm going to raise it to the 12th power. And we're going to round to, we said 4 decimals. 1, 2, 3, 4. Okay, so 0.06167. 7, round that 6 up to 7, or keep it at a 6. It's going to round it up to 7. Okay. This shows your compounded rate and how often. This shows what you're going to get annually, essentially. Okay. They're mathematically the same, though. All right. Anyone want to take a guess at how much money having $100 in this account for 10 years would be? Just a guess. Without using a calculator. You had to guess. You're earning 6% annual interest compounded monthly. $100 after 10 years. How much money do you think you're going to have? 6% is pretty high, by the way. 160? Any other guesses? Okay, 1,060. Any other guesses? I don't know what it is. We're going to find out together. 200? Let's take a peek. So if I want to figure out after 10 years, I'm going to take this formula and instead of X, what number am I going to write? 10. To the 12 times 10 power. After 10 years, this $100 is going to turn into $181.94. Okay. If you get a savings account that has 6% annual growth, you need to let me know. Because I'm going to take all my money out of everything I have and I'm going to go put it in that savings account. Because 6% growth is pretty high. Anybody know? I don't know what the actual average is, but anybody think they know what percentage you're going to get in the savings account? Lower than 2. Lower than 1. Yeah, it's going to be quite a bit less. It's going to be less than 1%. Okay. All right. But just for the sake of example, I think these problems are good. Okay. Any questions about 3A that I knew is compound interest? Okay. Let's take a look at problem B. Here's a really good thing about problem B or 3B. we kind of already did the work for this. So that's kind of why I front loaded it. So we get a little extra reps with that. Okay, the table shows a balance of money of a money market over time. We're going to write a function that represents the balance after X years. And then we're going to compare the balance in 3A, and then we're going to find the balances in 3A, and we're going to write them here, and then we'll go compare and contrast. Okay. First off, growth or decay? Growth. How can we tell? Okay, so this is growth. Okay, and because the money's increasing. How can I tell if it's compounded once a year or like monthly? Years are only going up by one, right? It's not going up by an increment, that's it. So this is just regular exponential growth. So this is my function. What's my A value? $100. So this person's putting the same amount of money in this account as the person in the above put in their account. All right. What about the rate? All right. I'm going to try to give you a tool. I'm going to show you how to do this in the calculator and figure it out for you. But think, doubling your money is 200% growth. We're going from 100 to 110. What kind of growth would that be? Okay, let's find out. 110 divided by 100. Okay, so it's 1.1. Okay, so hold on. That's just the B value. So in this one, we know that this part here is equal to 1.1. Do you guys see how I did that? I went 110 divided by 100. You could have done 161.05 divided by 146.41. And when you round that, because money only goes, it's 101.1. Okay. Okay. So then what is it? Minus 1. So this one has 10% growth. All right, that's part A. Any questions? Okay, anybody want to make a guess? What's going to be better? 6% annual interest compounded monthly, or 100% or 10% compounded once a year?
6%.
6% monthly over 10%. You're getting 4 more percent.
But it's monthly, so
It is happening more times. Okay, let's find out. Okay, so what we're going to do here is this is 3A. We're going to do the balance of 3A. We're going to find out. We're going to compare and contrast which one here is the better deal. All right. Well, 0 should be easy because we know that this is starting at $100. I'm not going to type that in the calculator. Let's do the next one. Next one here. 100 times 1.005 to the 12 times 1 power, because my first one for year is 1. I'm using the formula we wrote above. Okay, so this formula in red is what I'm using. I'm making sure I typed everything in correctly. 106 17. Okay, so then now what we're going to do is we're going to do the same thing, but instead of 1 year, now we're doing after 2 years. 112.72. Money, you round to 2 decimal points. I don't know if I needed to explain that or not. How do I type it in again fast? Like out, just out of the way? Okay, yeah. Yep. Okay, after 3 years, 119.69. Second enter. 4 years, 127.04. Or no, 05, if I went around correctly. And after 5 years, 134.89. You know, what you all said about you're compounding it more times in a year made a lot of sense to me. You know, that seems like a recipe, but why did this one not? How come the 10% in this situation ended up being a better deal? Remember what we did here? We took our compounded monthly formula and we kind of converted it into a yearly annual interest. And what's the yearly annual interest here? It's only 6%. So although I'm getting, or it's a little bit more than that, although I'm getting 6%, it's compounded monthly. So I do get more than 6%, but just not a ton more. Okay. So when you convert it into this, that's why I did this. You can actually see without ever making a table, I already knew that this was going to be a better deal by actually quite a bit. A little bit less than 4%. Okay. Questions about that? All right, we have one more problem. I think this will actually be a pretty short one, and then we're on the monitoring progress ones. Okay, the value of a car is 2,000. That should be a comma. 21,500. It loses 12% of its value every year. Okay, just one more to go, folks. We're going to write a function that represents the value in dollar of the car after X years. Growth or decay? Decay, because it loses value. What's the A value? How much am I starting at? It's the R value. What's the percent rate I'm losing every year? 12. I need that as a decimal, so 0.12. So now for part A, I'm going to write the equation. Y equals 21,500 times 1 minus 0.12 to the X power. Okay, you may have to take a calculator and type 0 or 1 minus 0.12 to get 0.88. And that's part A. All right. All right. I'm gonna have to step aside here in a second and look this up. if I want the yearly approximate monthly decrease, that means I'm gonna have to figure out how many times in a month it is, if it was compounded monthly. And I'm not sure if I take this to the 12th power and the outside to the 1/12 or the flip of that. So what I want you to do is just leave a little space here and then leave a little space there, and I'll go and look that up. I think it's 1/12 and 12th. You know what? I'm just going to go with that. 1/12 times 12 is 1. So when I go out to a power to a second power, this balances out and just gives me the same thing. So when I compound it 12 times in a year, if I take this to the 1/12 power, which is the 12th root, it's going to tell me what's the monthly percent that it's being. So you can figure out what that is. We're going to round to 4 decimal points. That seems right. So although it's losing 12% in a year, this kind of makes sense to me. It's losing a little bit more than 1% in a year. 9,894 to the 12x power. A little bit more than 1%, because it doesn't work linear. So it's not just going to be a 2% loss each month, because you lose a little bit and then the value that you have over loses a little bit, a certain percentage over and over again. Okay. Part C, find the approximate value of the car after 6 years. What's going to be equal to 6? After 6 years, what variable is equal to 6? X or Y? X. So then I just plug it into the formula. And just like when we graphed, you typed a lot of this stuff in the formula. 21,500 times 0.88 to the 6th power. Guesses after 6 years? Without using a calculator? $10. Well, it's 10,000 though. You're a little closer on the previous guess, I believe. So after about 6 years, the value of this car is going to be about, $9,984.69. And even then, I think a car, if it's just a typical car, is probably going to lose value after that. Okay. All right. What I would like everybody to do is spend a little time. There's 3 monitoring progress problems. I am going to wrap this video up, and I can have these up at the beginning of the next one. Here's your practice problems. 7 through 10, and then 13 through 18.